Where's an example of circular motion?
Mr. EJP, the movement of the moon around the earth.
The movement of the moon around the earth. Okay. Len, an example of circular motion.
Please, a car negotiating a curve.
A curve or bend. Thank you. A car negotiating a curve or bend. Amma, an example of circular motion.
Sir, please, an electric fan whirling.
Come again.
An electric fan whirling.
A rotating electric fan.
Yes.
Okay. Okay. Do we have more examples? Do we have more examples? Herbert, give me one.
The moon orbiting around the earth.
Yes, the moon orbiting around the earth. Don't also forget the motion of electrons around the nucleus. The motion of electrons around the nucleus. Then, when an object is tied to a string and whirled, if an object is tied to a string and whirled, the motion of the object also describes circular motion. Is that okay? All right. Now let's go into circular motion proper and look at the attributes of a body moving in circular motion. Here we are restricting our discussion to uniform circular motion. Of course, we also have non-uniform circular motion. But what we are looking at centers on uniform circular motion. When a body is said to be in a uniform circular motion, a body in a uniform circular motion moves at a constant speed v. Please, I mean constant speed. I'm not talking about constant velocity. They are not the same here. Okay. So a body in a uniform circular motion moves at a constant speed. However, we are representing the constant speed by the letter V. So under this discussion, when you see V, then we are referring to constant speed of the body. Now let's consider a body moving as such in a circular manner. There's the center of the circle C. This is the body. Of course, this is that fixed displacement of the body from the center. Instead of C, let me make it O, origin. This is the radius. Now, for the body to move from its initial position, which is this position, to any new position, so A, B, C, on and on and on, means that the body is in circular motion. So we are considering the body to have moved from a point A to B. So the body is now here. So this distance from the initial position A to the initial position B within the circle, we are referring to this distance as the linear displacement S. So the motion from A to B is the linear displacement within the circle or within the circumference, within the circumference. Now, let's assume the body moves from A, B, C, and then D, then finally E. Every movement of the body, okay, connects to a certain angle, which seems to be drawn or swept by the radius of the circle at the center. And this is what I mean. To move from A to B, we can connect this distance also to a certain angle which seems to be swept by the radius. Imagine this is the radius of the circle. The marker is the radius of the circle. Okay. To move from A to B, it's as if the radius is sweeping a certain angle at the center. Please, you see it? Please, class, can you see the demonstration?
Yes.
To
Yes,
move from A to B, it's as if the radius of the circle also sweeps or describe a certain angle at the center of the circle. From B to C, it's also as if the radius is sweeping an angle at the center. From A to D or C to D, the same thing. But we realize that as the angle, the linear displacement increases within the circumference, then the angular displacement or the angle which is swept at the center is also increasing. Okay. Now, when the body finally moves from A to E, the linear displacement is half of the circumference. It's half of the circumference of the circle. That is its linear displacement. But you also realize that the angle, which is also swept at the center, would also be from the A to E. So this will be the whole angle that matches the linear displacement. So the greater the linear displacement within the circumference, the greater is that angle swept at the center. So let's demonstrate this way. From A to B, this is the linear displacement. And this is the angle swept at the center, theta 1. From A to C, this is the linear displacement. This is also the angle swept at the center from here to this point, theta 2. From A to D, this is the whole linear displacement. And this corresponds to the angle swept at the center, which is, so as S increases, theta, that angle at the center also increases. And mathematically, what is that name given to such a relationship? A relationship where as one increases, the other quantity also increases. What's that relationship?
Direct proportionality.
Good. So we realize that S is directly proportional to theta. Okay. Now this angle swept at the center as a body is in circular motion. We call this angle as angular displacement. This angle swept at the center as a body, okay, is in circular motion is known as the angular displacement. Angular displacement. This is represented by the symbol theta. So I want somebody to, based on the explanation given, I want one of you to help me define what angular displacement theta is. What is the angular displacement of a body in circular motion? Yes, anybody to help us? Yes, just express your view. Herbert, go ahead.
I said the angular displacement. This is when the angle at the center increases when the body increases.
When the body something increases, qualify it a bit.
Okay.
All right. Okay, that is Herbert's view. Nice one. Any other view? How can you explain angular displacement to your younger sister or brother based on the explanation given? Carl.
Please, angular displacement is the angle described by a body moving on a circular path.
Okay. Thank you. Let me also bring in my view. So I would they explain it as the angular displacement is the angle swept by what sweeps the angle? By the radius of the circle at the center. So the angle swept out by the radius of a circle at the center. At the center of the circle. Okay, by the radius at the center of the cycle. So from the explanation, we see that as the body embarks, okay, on circular motion, that is moving from A to B, B to C, C to D, D to E, the radius as any transition within the circumference, which is the linear displacement made by the body, describe a certain angle at the center. Describe a certain angle at the center. And this angle, which is described or swept out by the radius of the circle at the center, is what we refer to as the angular displacement, represented by the symbol theta. Okay. The movements, the distance covered by the body within the circle from A to B, B to C, that is known as the linear displacement, represented by the symbol S, small letter S. So we realize that as the linear displacement within the circumference increases, the angular displacement at the center also increases. And so S, which is linear displacement, let me go word before we relate it to an equation. The linear displacement is directly proportional to angular displacement. Note that all linear quantities occur within the circumference. All linear quantities occur within the circumference, whereas all angular quantities occur at the center or the axis of the circle or axis of rotation. So we are measuring angular displacement from the center, linear displacement from the circumference. So S is directly proportional to theta. Any direct proportion or proportionality goes with a constant. So S is equal to a constant of proportionality times the angular displacement. And this constant of proportionality K is equal to that constant radius of the circle. So K is equal to R, the radius of the circle, which doesn't change. Therefore, S is equal to R times theta. Ladies and gentlemen, this is the relation connecting linear displacement within the circumference and angular displacement at the center of the circle. Please, are we okay?
Yes, please.
So a relationship connecting linear displacement and angular displacement. Don't forget that R is constant, which is the radius of the circle. If you have any question, please ask. If you have any question, please ask. Chrysler,
Yes, please.
is it crystal clear?
Yes, please. Just okay.
Okay. Alma,
Yes, sir.
are you okay?
Yes, please.
All right. Now, can I flip? Are you done writing what is here, or are you done?
Yes, please.
All right. I want to flip the screen. Now, class, what is the SI unit of linear displacement? What's the SI unit of linear displacement? Or displacement?
Length.
SI
Meter.
units. Good.
Meter.
Good. So displacement, okay, has SI unit as the unit for measuring length, meter. Now the SI unit of angular displacement, SI units of angular displacement. Can somebody tell us SI unit of angular displacement? Can somebody share with us? Okay, this is known as the radian. Radian. Okay, don't forget the meter, which is the SI unit of linear displacement, is shortened as, how do we denote the unit meter? Or how do we express this?
M.
Herbert, be specific. Is it any M?
Sir, no.
So qualify your M.
Sir, for the meter.
Yes. What M? Is it capital M or small
Answer
letter?
small m.
That's the qualification I want from you. So
Okay.
small letter m. For radian, its denotation or representation is RAD, rad. And you see this on your calculator. It is another angular measurement, the SI unit. You often use the degree. Yes, the degree is another form of angular measurement, but that is not the SI unit. The globally accepted unit for angular measurement is the radian. When you are saying it radian, when you are writing it rad. So if you have to say it, I don't want to hear rad. Say radian. When you are writing, then you rad it. Is that okay? So other units of angular measurements, other units of angular measurement, apart from the SI unit, we also have degree, which you are so familiar with, shortened as that small zero at the uppercase. Okay, and we also have the revolution, which is shortened as rev. Just as you can convert from meter to centimeter, meter to millimeter, and all that, we can also convert this angular measurement from maybe radian to degree, radian to revolution, or degree to radian, and all that. Please, are you with me?
Yes, please.
So let's look at how we can effect this conversion from one angular measurement unit to another.
Mr.
So
Dia,
hello.
it's fine. It's already clean. The down part I couldn't see. It was blurred.
Really?
That's yes.
Lizzie, don't worry. The
That's
video will come.
okay.
Mm. I'm going to draw to give you an outlook of how to do this conversion. If a body starts from a point A, goes through it, and then end. What is the name given to this total distance covered during the complete rotation or revolution of the body? What's the name given to this total distance covered?
So the circumference.
Good. How do you calculate for circumference of a circle? How do we calculate it? You said C, circumference of a circle, is equal to what? 2 pi r. So the circumference of a circle is equal to 2 pi times the radius of the circle. So knowing the radius of the circle, when you multiply by 2 pi, you have the total distance surrounding this circle. Now, we've also established that linear displacement is equal to radius times angular displacement. Okay. Now, if the body goes through one complete revolution, starting from a point A and then coming back to a point A, S. So for a complete revolution, that is going round the circle once, for a complete revolution, the linear displacement S is equal to the circumference of the circle. True or false?
True.
True.
Good. So for a complete revolution, the linear displacement within the circle will be equal to the circumference of the circle. And so we can argue that, okay, if S is equal to C, then this side must also be equal to this side for a complete revolution. So R theta is equal to 2 pi R. Since the radius is the same, then we argue that theta will be equal to 2 pi. Now this theta is angular measurement in degree, and then this is angular measurement in radian. So when a body makes a complete revolution, the angular measurement in degree, which is 360, okay, starting from A and then ending at A, the angle described at the center, which is theta, at the angular displacement, is equal to 360 degrees. This 360 degrees is equal to an angular measurement of 2 pi radian. So this is the conversion equivalent. One complete revolution in degree is equal to 360. A complete revolution in radian is equal to 2 pi. If we have half of a complete revolution, for half of a complete revolution, starting from A and then ending at A, ending at B, theta will be equal to, so what will be theta if the body goes through half of a revolution? What will be the angular?
180.
Good. So
180.
good. This is 180 degree. If 360 is equal to 2 pi radian, then 180 degrees will also be equal to what in radian? Yes.
Say pi. Oh,
It's, He's saying pi. Priscilla, what is your view? If 360 degree is equal to 2 pi in radian, 180 degree would also be equivalent to what in radian?
Mr. Deputy talking to me.
Yes, Priscilla. If
Please come again.
If 360 degree is equal to 2 pi radian, what would 180 degree give us?
I think it will be pi radian.
It will be pi because 180 is equal to 360 divided by 2. And so if you want to get its equivalent, you also divide 2 pi radian by 2. So this is how to convert from degree to radian or from radian to degree. Please, are you okay?
Yes, please.
Please let me hear from the rest of you. I have Equia, Abba, Herbert, Abba, Equia, Amma, Asmani, Carl, Priscilla, Effie, Rama, Lizzie, and Lynn. The attendance today isn't encouraging. Anyway, today is starting the maiden edition. So now, sorry, let me clean. Yeah, by you there. Oh, yeah, by is gone. So we've just established that 360 degree is equal to 2 pi radian. Please, this is also equal to either you express this is degree, this is radian. Okay. Either 2 pi or this is also equal to, I can also substitute the value of pi. Pi is 22/7 or 3.142. So I can substitute 3.142 multiplied by 2 and have the degree equivalents also in radians. So I can say that 360 degrees is equal to 2 pi radian, and it's also equal to 6.2. Is it 23? Calculate for me. 6.23 or 28?
28.
28 radian. Either you express it in multiples of pi or in decimal. Okay. Then, so 1 complete revolution is equal to 360 degree, and it's also equal to 2 pi radian or 6.28. Okay, let me give you a question quickly. Convert, Lane, this is your question. 30 degrees to radian. This is for Lane. Krista, yours is, you have to convert pi on 2 radian to degree. Carl, you are converting 2 revolution to degree. And then 120 degree to 2 radian. Aquia. Anyway, let me give the whole work to all of you. So this is what you have to do now. Let me add another one. For convert 4.28 radian to degree and convert 540 degree to radian. This is the problem of the day. 5 minutes, start work. Everybody. So I've moved from Lane, Chrysler, and Co. It is for all of you.
Stadia.
Hello.
Stadia, please. It's like you're frozen on my screen right now. Can I get what you just said?
The question.
Yes, please.
You mean I'm frozen on your screen? Or is it?
Yes.
I'm not frozen. I'm not frozen.
Okay, I'm moving now.
So do I send it to the group?
No,
Okay.
please. It's okay. Thank you.
No, let me still drop it in the group. Maybe others also have that challenge. Finished?
No, sir.
Oh, 5 minutes. Oh. Aduma, you are sitting there quietly without even coughing. Okay, so Akuya, what do you get for question 1? Convert 30 degrees to radian.
0.52.
Pardon?
0.52 radian.
0.52.
Yes.
Akuya, give it to me in multiples of pi before you express it as decimal. Give your answer to me in multiples of pi before.
6 pi.
6. Akuya, did you say 6 pi
Pi. 1 over 6 pi.
or pi on 6?
Yes, please.
Good. So 1 on 6 pi or pi, which is 3.1442 over 6. And I'm sure this is what you called for me earlier. Is that right?
Yes.
So or 0.524 radian. Please, did you get this?
Sir, please
Yes,
no.
please. Yes, please.
Okay, Herbert, you didn't get this.
Yes.
What did you get?
Sir, please. Now I want you to explain it.
Okay,
Explain
see,
it again.
You see, 360 degree equal 2 pi radian. So
Yes, sir.
even if you should do it gradually, okay, if you divide this by 2, you have 180, and this will also
Yes,
be
sir.
divided by 2. So 180 degree equals pi radian, which is also 3.142 radian.
Yes, sir.
If I divide 180 by, what do I have to divide 180 by to get 30? What do I have to divide 180 by to get 30? All right.
Yes, sir.
180 divided by what would give us 30 degrees?
Sir, 6.
Good. So 180 divided by 6 would give me 30. And so pi divided by 6 would also give me, okay. So,
Okay, sir.
or this divided by 6. So 30 degrees equals 1/6 pi radian, or this is also equal to 0.524 radian. That's how to, once you have
Okay.
not so, hey, okay. Then, Len, what did you make for question 2? Convert pi on 2 radian to degree. What did you get for this?
Please, I had 90 degrees.
Okay, exactly. Because pi is equal to, pi in degree is 180. So this is 90 degrees. Okay. Lizzie?
Mr.
Lizzie?
Yeah.
Convert 2 revolution to degree. 2 complete revolution. Convert this to degree for us. What did you score? Or you are not true.
720 degrees.
Exactly. Because 1 revolution is 360. So if 1 revolution is 360, then this will be 360 times 2, 720 degrees. Exactly. All right. Carl.
Yes, sir.
120 degree to radian.
2.1 radian.
Or give it to me in multiples of pi first before expressing it in decimal.
Uh,
If any of you did that, please share that with me. 120 degree expressed in multiples of pi. Yes, Abba.
Sir, please. 2 pi over 3 rad
2 pi
over
over
3
3.
radian.
Okay, so let's see if Abba got it right. So if 360 degree equals 2 pi radian, then 120 degree, will it be more or less? Watch you. If 360 is giving us 2 pi, what 120 would give us? Will it be more or less than this one?
So it will be less.
If it will be less. If less, more divide. So if this will give us less, then we divide this less by this more. So 120 over 360 times 2 pi. So this 12 goes into 36, 3. So this will be equal to 2 pi over 3 radian. And that's exactly what Abba called for us. So you can use ratio and proportion. If I should even give you 540 degrees, convert this to radian. By using a ratio and proportion, if 360 is giving us 2 pi radian, then 540, will this be more or less?
More.
It will be more. If more, we divide this more, 540 by this less. So 540 divided by 360 times 2 pi. Then we do our cancellation, then oh yeah, we are gone. Please, do we understand? So
Yes,
the
please.
Yes,
conversion isn't so difficult. All right, then the other question. You have to convert 4.28 radian to degree. Yes. Who was able to go through that? 4.28 converted to degree. Yes. Who was able to get that?
Sir, please, the
Okay.
question again.
I asked you to convert 4.28 to 8 radian to degree. Abba, how did you do it?
Sir, please, from your last formula, you said 360 degrees is also equal to 6.28 rad. So I
Yes.
did, if 360 is equal to 6.28 radian, then
Exactly. Ratio and proportion. Okay. So I said 360 is equal to 6.28 radian. Even 180 would give us 3.142 radian. So if 360 or 180 degrees is giving us this, then it's like this time around, having given you this value in radian, express it in degree for us. So use ratio and proportion. 180 is to 3.142, or you can use 360. Okay, then 4.280 is to unknown. So 180 divided by 3.142 must be equal to x divided by 4.28. Then you make x the subject. X is equal to 180 times 4.28 divided by 3.142. And the calculator would help you out. So Abba, what did you get for that?
sir, please, I had 245.35 degrees.
So approximately 245 degrees. Approximately 245 degrees. Plus, are we okay?
Yes, please.
And the last question.
Answer, sir.
Hello.
Sir, please, for that, the question that she had, the answer is 245 degrees.
Yes.
I had 248. So is it the same or?
It's because of what you use as pi. Don't forget, I have made an approximation.
Okay.
So if you use the whole value, it will change. I have just approximated it.
Okay. Okay.
All right. Then the last one, I think 540. 540. Effie. Effie. Effie, are you there? Effie, I have to call everybody. Oh. Okay, Len, what do you make for 540 in radian?
Please, I had 9.43
9.43
radian.
Give it to me in multiples of pi first.
3 pi.
3 pi radian. Okay, let's see. So if 360 is equal to 2 pi radian, then 540 must be equal to more. If more, let's divide. So 540 over 360 times 2 pi. This is 18. What is 54 divided by 18? Do that for me. 54 divided by 3. Okay, good. So this is 3 pi radian. So that's it. How to convert from radian to degree, degree to radian, and then to revolution. So simple. Let's continue our journey on circular motion. And please, do you have any question? No question. All right. So you have, I think you have understood what angular displacement is. The angle swept out by the radius of a circle from the center of the circle. So when a body moves from A to B, this angle at the center, theta, is what we are calling as the angular displacement. There is the linear displacement. And what we have here is the radius of the circle. There's the center. Okay. Now, when the body continues to move within the circle, from A to B, B to C, C to D, on and on, you realize that not that it would take the time taken for the body to move from A to B, and then the time taken by the body to move from B to C, it will take different times to get to every point. A to B, maybe it will take T1 to move from A to B. To move from B to C, it will take the time T2. To move from C to D, it will also take the time T3. What we are witnessing is this. As the body embarks, okay, in circular motion, we realize that the linear displacement of the body continues to change with time. So, a body involved in circular motion has its linear displacement change with time. So as its linear displacement changes with time, the same or simultaneously, its angular displacement also changes with time. And look at this. From A to B, this is the angular displacement, theta. Let's call this theta 1. Now, from A to C, the angle is widening out, theta 2. Within this whole time, from A to D, theta 3. So, as the body continues to be in circular motion, its linear displacement or position within the circle changes with time. In the same instant, its angular displacement at the center also changes with time. Please, are you with me?
Yes,
Are you
please.
clear?
Yes.
Yes, please.
Okay. So a body involved in circular motion has its linear displacement change with time, and its angular displacement at the center also changes with time. In linear motion, when we have a change in displacement with respect to time, this amounts to what? A change in displacement with respect to time amounts to what in linear motion? So we have velocity. So it means that as the body's linear displacement s changes with time, it amounts to linear velocity within the circumference. Linear velocity v within the circumference. So why is it that a body in a circular motion has a constant linear velocity v? It is because its displacement continues to change with time. So once its displacement within the circumference changes with time, it amounts to linear velocity. But this linear velocity occurs within the circumference. Now, at the same instant, we realize that as its displacement changes, its angle at the center also changes. So we have change in angular displacement theta with respect to time, giving us time interval, giving us what we call angular velocity, represented by the letter omega, what you see as W. Okay, so as the body's displacement position within the circumference changes with time, it amounts to linear velocity within the circumference. In the same way, it's a simultaneous thing. They occur, both occur at the same time. As its position is changing, we realize that its angle at the center is also changing with time. So it also gives us the angular velocity of the body at the center. So the linear velocity is as a result of the changing position of the body. Or linear velocity velocity v of the body is as a result of changing position of the body within the circumference. And the angular velocity is as a result of the changing angular displacement at the center of the circle. And these two quantities occur at the same time. As the body's position changes, it affects the changing angle at the center as well. Please, are we okay?
Yes, please.
So these are the technical parts of it. When you understand this, oh, you are good to go. So it's similar to linear motion. When displacement or position of the body changes with time, we have velocity. Okay, so it's like this. If the body comes to this point, we have linear velocity v. Why? Linear velocity v because its position has changed from A to B. And this will also be affected by the changing angle because initially, when it was A, the body was at A, its angular displacement was what? I want somebody to help me. If the body is at A and hasn't moved, what will be its angular displacement?
Zero.
It's zero. Okay, it's zero because it has not moved. Now, the moment it moves from this point to this point, you realize that because of the change in position, there will be a corresponding change in the angle at the center. Okay, so as the body's position changes, it affects its angular displacement at the center. And so the changing angular displacement gives us what we call angular velocity. So I want somebody to help me understand what angular velocity is. Lizzie, over to you. Lizzie, what is angular velocity omega? Lizzie? Oh, is Lizzie gone? Oh, I'm frozen.
Yeah, please, I'm here.
Lizzie, what do you understand by, in your own way, what do you understand by angular velocity of a body in circular motion? Lizzie, are you engaging your brain?
Yes, please.
Okay, Priscilla,
Yes, teacher.
what is angular velocity omega?
Teacher, I'm coming.
You are coming, eh? Amma,
Yes, sir.
what is angular velocity?
Sir, please, angular velocity, it is the time rate of change of angular displacement.
Thank you. So the rates of change of angular displacement with respect to time is what we call or refer to as angular velocity, or as Amma said, the time rate of change of angular displacement. So mathematically, we said omega is equal to delta theta over t. Omega is equal to delta theta over t. The delta indicates a change, the change. Akuya, Adoma, what's the SI unit of angular velocity?
Rad per second.
Eh?
Rad per second.
No. Say it well.
Radian per second.
Radian per second. I said when you are saying it, it is radian. When you are writing, it is rad. So the SI unit of omega is radian per second, which is shortened as RAD okay. There can also be other units. Don't forget there are other units for angular measurements. So you can also be given other units such as revolution per minute, degree per second, or degree per minute, degree per hour. So when you see in circular motion, when you see RPS, this is revolution per second, or sometimes radian. Okay, when you see RPS, RPS means radian per second. Then when you see rev, we are referring to revolution per second. When you see RPM, this is either radian per minute or rev per minute. Usually, because the radian is the SI unit, we don't shorten it. So usually when you see RPM, revolution per minute. But I said it can be, since time can be seconds, minutes, hours, you can see per minute, per hour, per second, per day. So open your eyes to this unit. Is that okay? I'll send you some works under this today so that you master. All right. So that is it with angular velocity. Now, if you recall, I gave you the relationship between linear displacement and angular displacement. And about what's the relationship between linear displacement and angular displacement?
Say please, linear displacement, which is S is equal to
S
theta r, and
so
r is the constant.
R theta. So S is the linear displacement.
And theta is the angular.
Good.
displacement.
Theta is angular displacement. And R is the radius, that constant radius. So there is a relationship for linear and angular displacement. We also have a relationship connecting linear velocity V and angular velocity. I said they occur as twins. When there is a change in the position of the body, there will certainly be a change in the angle covered by the body at the center. So they are a joint kind of thing. So let's also look at the relationship between linear velocity and angular velocity. We can develop that relationship from S is equal to R theta. I earlier said that as a result of the change in position of the body with time, we have what? Yes, completed for me. As a result of the change in position of the body with time, what we have? I'm waiting. I'm taking it again. Please pay attention. As a result of the change in the position of the body with time, what we have? Hello.
So we have the angular velocity.
I take it again. As a result of the change in position of the body with time,
Okay.
what we have?
Linear velocity.
Linear velocity. Then, as a result of the change in the angle covered by swept by the radius with time, what we have?
Angular velocity.
Angular velocity. So S and theta all occur due to, they happen due to what? S and theta changes due to, or with respect to?
Time.
Time. So divide both equations here by time, because the changing time would affect this as the position and the angle at the center change. So divide both by time. When you divide both equations by time, what is S over T? What is S over T?
So the linear velocity.
Linear velocity. Linear velocity. So this, the left-hand side gives you V. Then you have R times theta over T plus, what is theta over T?
Say
So
omega.
the angular velocity. That's omega.
Exactly, angular velocity. So we have V is equal to r omega. And this is the relationship between linear velocity and angular velocity. The relationship between linear velocity v and then angular velocity omega at the center. Are we okay?
Yes.
Okay. Now, there is another quantity. Take when you on a fan, okay? No fan works in such a way that the moment you on the fan, then the fan would attain its maximum speed. As soon as you on it, no, it doesn't work like that. Especially when the fan becomes old, when you on it, you hear the noise, kukru, 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 gradual, then it will build up its maximum speed. True or false?
True.
So when you take the blade of the fan, initially, its distance covered will be slow. Assuming the marker is the blade of the fan, you realize that when you on it, it will be covering small distances. Then as time increases, the distance covered within the circumference will be increasing. Then the angle swept at the center or the axis will also be increasing. Then you realize that it will have its full speed. What it means is that the changing distance or circumference will give you the speed, v. The changing angle at the center with time will also give you the angular velocity. Now, as time increases, you realize that it will cover greater distance along the circumference. And so its speed would also increase. As its speed increases, meaning it will also cover a greater angle at the center. And so the angular speed would also increase. So a changing speed at the center with time would connect to a changing angular speed, okay, at the center with time. So when the speed v within the circumference changes with time, it amounts to angular linear acceleration within the circumference. Okay, so a changing speed with time gives us linear acceleration within the circumference. But in the same vein, a changing angular speed at the center also amount to angular acceleration. So the next thing to look at is angular acceleration. Sorry, angular acceleration and a linear acceleration. So as the speed of the blade of the fan increases with time, we'll have acceleration within the circumference. Now, as this speed increases, it will affect the angular displacement at the center and will also change at some rate with time. And so that would give us angular acceleration at the center. So the linear acceleration is as a result of a change in speed v within the circumference. Then the angular acceleration is also as a result of the change in angular velocity or angular speed omega with time at the center of the circle. So we define angular acceleration. Please, angular acceleration is represented by the symbol alpha. So learn the symbols. So angular acceleration is the rate of change of angular velocity omega with time. Class, is it understood? Hello. Are you there?
Yes,
Please,
sir.
yes.
Okay. Len, help us determine the SI unit of angular acceleration. The SI unit of angular acceleration. The next.
Please, radian per second square.
Thank you. So this is radian per second squared. Len, what about linear acceleration?
Please, it's meter per second squared.
Good, good. So that's it. But note that for angular acceleration alpha, there can be other units such as non-SI units. I mean, we can also have revolution per second squared, radian per minute squared, even radian per hour squared. You can also be given degree per minute or degree per second to convert to SI units. So I can give you a question where the angular acceleration can be in degree per minute squared or degree per second squared, and as that you convert it to SI unit, which is radian per second squared. So get ready for said questions. Okay, at least all to help you to reason so well. Okay, I want somebody to help me in doing this. I want us to establish the relationship between linear acceleration A and angular acceleration alpha. Help me out to determine the relationship between linear acceleration A and angular acceleration alpha. Yes. A volunteer to help us. Just discuss it with us. How do we do that? Anybody to volunteer? Oh, just anybody to try, or somebody to just try. You may not be so exact, but I just want to try. How do we get the relationship between A and alpha? Do I call Akuya Doma? Akuya,
Lydia.
yeah, it's over to you. The relationship between linear acceleration E and angular acceleration alpha.
Acceleration is equal to linear acceleration is equal to angular acceleration time.
Okay, how did you get that? Okay, how did you get that? Yeah, she's
So
saying
they are
that.
the changes.
Mhm. Okay, I'm listening. Okay, I'm listening.
So they are the first relation.
Hmm?
A is equal to R, V is equal to linear velocity is equal to R times angular velocity
Mm-hmm.
with respect to time. So V
Mm.
over T is equal to R omega all on T.
Okay, thank you. So you see, the issue is about what brings up this. How do we get linear acceleration? It is when the linear speed of the body increases. When V increases with respect to time, we have A. So we'll have A when there is a change in V over T. When do we have alpha? When angular velocity at the center changes with time, we have angular acceleration. So you divide this both by the changing time, and this will give us A is equal to then R times omega T. This part is equal to this one. So R alpha is the relationship. Okay. Please note that all linear measurements takes place within the circumference, and all angular measurement takes place at the center of the circle. Carl, what did I say? Carl,
You said all linear measurements take place at the circumference and all angular measurements take place at the center.
exactly. So linear displacement, linear velocity, linear acceleration all occurs within the circumference. And angular displacement, angular velocity, angular acceleration all occurs at the center or the axis of rotation of the circle. Please, is it difficult? Is it difficult? Do I have people in the house?
Yes, please.
All right. All right. Another time. Let me look at the time and then. Okay. Let's look at. Let me get a few questions. Okay. A few questions for you to answer. At least today is our first meeting, so something to think about, maybe 2 or 3 questions, then we end for today. 29. All right. Convert 72 revolution per second convert 72 revolution per second to radian per second. To radian per second. Then you are also to convert 1.50 times 10 to the power 3 RPM. This is revolution per minute to radian per second. This is revolution per minute, RPM. The last one, I. Convert 2.000 radian per second to degree per second. Just think through in about 5 minutes time and share your answers with me.
Mr.
What did you make for I?
114.64 degrees per second.
That's correct. 114.6 degree per second. Yes, let's together look at it quickly. Maybe
No, it's one that's correct. Out of three. I understand, but some of them he hasn't taught us. It's now come to teach us, right? So we should just try and see if we can work it.
Herbert, we can hear you. So hello, can you hear me?
Yes, sir.
Let's quickly solve it. So we have 72 rev per second to be converted to radian per second. Since the numerator is already in SI units, you don't worry yourself. I said numerator, denominator. So you need to think of converting 72 rev to radian. And how do we do that? I want to convert 72 revolution to radian. How do I do that? Yes. Anybody to help me? Let's hurry up. How do I convert 72 revolution to radian? Yes, Abba.
Sir, please, 1 revolution is equal to 2 pi. So 72 will be equal to 72 times 2 pi,
Thank you.
which is approximately 452.4 rads per second.
So this is 72 times 2 pi radian. And when you substitute 3.14 for pi, you have 152 radian. The denominator is already in seconds, so that's it. Then II.
Sir, please, is 400.
Let me confirm. Okay, so 72 times 6.28. 452. Thank you. .2 radian per second. Then II we have, this is 1.5 times 10 to the power 3. And this is the same as 1,500. But we have revolution per minute. And our task is to convert this to radian per second. Here we have issues with both numerator and denominator. This numerator is not an SI unit, then denominator. So let's convert the numerator. We have 1500 times 2 pi, and 2 pi is 6.28 radian over, this is 1 minute, and 1 minute in seconds is 60 seconds. So multiply numerator, divide by the denominator. And so when you do that, we have 1,500 by 6.28, which is 9,420 divided by 60. And so this amount to 157 radian per second. Then lastly, we have two radian per second. So 2 radian per second. And our task is to convert this to degree per second. Okay. 6.28 radian is equal to 360. So if 6.28 radian is equal to 360, now we have 2.0 radian. Will it be more or less? Will it be more or less?
So it will be more.
I open your eyes. Oh, if
Mm.
6.28 is giving us 360, 2.00, will this be more or less?
Less.
That will be
It will be
less.
less. If less, you divide by this more. So 2 divided by 6.28 times 360 degree, and calculate that for us. So 2 divided by 6.28, which is this, times 360. And this is giving us approximately 115. Approximately 100 and it's 114, but we can approximate this to 115 degree. Plus, is it understood? Is it understood? Are you okay?
Yes,
Hey,
please.
do I have learners in the house?
Yes, please.
Okay.
Yes.
Then this is where I draw the curtains on today's meeting. Please, I'll upload the video soon, so you can go back to it and then look at where you missed. If you have any question, quickly ask. If you don't have any question, then in fact, take care, and then have a very wonderful weekend. Please do inform your colleagues that for physics, we've started so well. We'll be running at the speed of light until Tuesday. In fact, bye-bye.
Bye.
Charlotte, the late
Yes, please.
Charlotte, the late. I'll send you the video.
Thank you so much.
Okay, yo.